last time we were talking about Roman columns of neon, and we did some idealization of one of the columns, and we saw we can calculate the external forces, and we can also calculate reaction forces using equilibrium equations, and we can also calculate the internal forces. Now, uh, we saw last time that this internal force, which we were calculating before, is an actually a resultant of force. So actually, what happens is that the entire area is actually resisting that external force. So you have a distributed forces, and we were calculating the resultant of those distributed forces as an internal force. So this is what actually happens. You have like all the distributed forces which is resisting the external force, and you can, so you have to also consider the area where the force is acting. So when you do that, you get a term which is called stress. So stress is basically force divided by area, and that's the formula for stress. And this way of looking stress is called macro scale stress or an average stress approach. There's another approach which is called a micro scale approach. In micro scale approach, what we do is that we take a very small particle and we zoom out. We call this particle stress element, and we can also see that what are the forces and stresses which are acting on that stress element. So in that case, only one force is acting, so we can calculate the stress, or we can see the stress from a micro scale approach as well. And this cube which we have extracted is called a stress element. And the formula is the same, basically force divided by area. So that's the definition. So stress is defined as force over an area, so force divided by area. And there are two type of stresses. You have a normal stress and you have a shear stress. And the difference between normal stress and shear stress is that in normal stress, the force is acting perpendicular to the area of concern. And in a shear stress, the force is acting parallel to the area of concern. And these are the formulas for shear stress and normal stress. So formula is same, force divided by area. But in normal stress, the force is acting perpendicular to the area. In shear stress, the force is acting parallel to the area. Now, if you look into a stress element, so on a stress element, basically you can see nine type of stresses. So three are normal stresses and six are shear stresses. So this stress X is a normal stress because this stress is acting perpendicular to the surface area. This stress is also normal stress. This stress Z is also normal stress. And the other stresses, they are acting parallel to the surface area. So these stresses are called shear stresses. So these are the formulas for normal stress and shear stress. We're gonna look this into detail in later chapters. We also saw when a force is applied, it's gonna create elongation. So elongation is basically change in length. That is like final length minus the original length. So you can calculate the elongation. So if you divide this elongation with the original length, you're gonna get a term which we call normal strain. So normal strain is basically change in length divided by the original length, or elongation divided by the original length. So like you have two type of stresses, you also have two type of strains. So you have a normal strain and you have a shear strain. So normal strain is because of the normal force and the normal stress. And when you have a shear force, you're going to have shear strain because of the shear force and shear stress. And what shear strain does is that it actually distorts the shape. It creates an angular distortion. So this angular distortion can be seen in this figure. So you have a force acting in parallel to the surface area. And because of this, you're not going to have elongation, but instead you're going to have angular distortion. So this angular distortion can also be calculated. So this is shear strain. Shear strain, the formula is same, change in length by the original length, but change in length is actually lateral. So in this case, if you have to calculate the shear strain, that is ux divided by the original length, which was like L naught. And we also saw what happens when we put a material, sample material, in a machine, and we try to see what are the stresses and strains when we keep on applying the forces. And what we get is a stress strain curve. So when you put a material and a sample of any material in a machine, and you apply a force, and you keep on increasing the force, and you keep on measuring stresses and strains by using these equations, you're going to get some stress strain curve. And this stress strain curve is specific for all the materials. Like for any material, this is specific. So this stress strain curve is for a specific material, let's just say steel. So you can see when you keep on increasing the forces, you're gonna keep on increasing stresses and strain, but in the elastic region. So in the elastic region, the stresses are directly proportional to strain. So if you keep on increasing the force, you're gonna keep on getting increased stresses and strains, but till a particular point. And then after that, you're gonna see a plateau. So this region where you will see stresses and strains directly proportional to each other is called an elastic region. And we are concerned about this elastic region. In this course, we're going to just talk about elastic regions. And if you apply a force greater than the stresses, and you go beyond the elastic region, then you will be in a plastic region, and in plastic region you're going to see permanent deformations, and we don't want that. I mean, we don't want a material to have permanent deformation. So we'll make sure that the stresses are below the yield stress. So that's the yield stress. That's a very important point. So we'll not exceed the forces to a point where you will have stresses higher than the yield stress. So that's yield stress is a material property. For every material, you have a specific yield stress, and we don't want forces to go beyond the yield stress, because then we'll have permanent deformation and we're going to have problems. Also, if you keep on increasing the forces, ultimately it's going to fracture. So that's the point. If you keep on increasing the forces, it's going to go from elastic region to plastic region, and from plastic region you're going to see some strain hardening, and then ultimately necking, and then ultimately your material will fail. So for a material to actually like fracture, it takes a very large amount of forces and very large amount of strains. But for our purposes, we'll not exceed the elastic limit. And most of the structures, if you exceed the elastic limit, it considers that it's a failure. So for example, buildings, you don't want stresses to be so high that uh, the stresses are more than the yield stress of steel or concrete or something like that. And then if you have stresses more, then you're going to have permanent deformation, like you'll see deformations permanently. So that's the elastic region, and we'll stay below the elastic region. And different materials have different stress strain curves, and you can know a lot about that material by looking at the stress strain curve. For example, you can see this bone material. You can see it can only take 200 megapascal of stress. So if you apply force that will result in stresses more than 200, then it will fracture, the bone will fail. And also it can take a very less strain, so it cannot elongate much. So the bone is a brittle material. But if you see steel, or if you see this steel or this steel, it can take a lot of stress. So it can take a lot of force, and but it cannot take a lot of strain, so it's not going to elongate much. But if you talk about this steel can elongate a lot, so it can stretch a lot before it fails. Same with the copper can stretch a lot before it fails, but copper cannot take a lot of stress. It can take 200. So the amount of force needed to break bone or a copper is about the same, but you have to apply a lot of force to break the steel. And for this steel, you have to elongate the steel a lot before failure. So that's how you can see stress and curve, and you can know which material will behave how. So for example, in this case, bone is a brittle material. It will not elongate, it will just break if you apply a force. But copper and steel, they are ductile material because it can take a lot of elongations. So that's how you can know how material will behave. And we also talked about Poisson ratio. So Poisson ratio is ratio between the longitudinal strain and the transverse strain. And this is also a material property. For every material, we already know what Poisson ratio is. So if we can calculate strain in one direction, we can use this Poisson ratio and we can calculate the strains in other direction. So basically, if you apply a force, you're going to see compression in the direction where you're applying force, but you're going to see like elongation in the other two directions. And the ratio is constant for these. So that ratio is called Poisson ratio. we will do calculation and then we'll like understand more about this. So what is Hooke's law? So we already have calculated, we have already seen stress strain curve for different materials. So we know if we keep on increasing the force slowly, so you're going to see increase in stresses and strain till a point, and this region is called elastic region. And then after that, you have plastic region, strain hardening, ultimate stress, and then you're going to see fracture. But we are only concerned about elastic region. So we'll not go beyond elastic region. We'll not apply forces which will extend the material beyond the elastic region. So in an elastic region, you can see it's a straight line. So in this elastic region, you can see the stresses are directly proportional to strains. Like if you apply a force, stresses are also increasing, strains are also increasing, but they are all only increasing till this point, which is yield point. After that, they become straight. So for an elastic region, stresses and strains are directly proportional. So that's what Hooke's law says. Hooke's law says in an elastic region, stresses are directly proportional to strains. And you can remove the proportionality and you can put an equal sign, but you have to also add a constant to it. So this is what Hooke's law says. Hooke's law says that in an elastic region, stresses are directly proportional to strain. And we can also see this from the stress strain curve as well, that the stresses are directly proportional to strains. So that's Hooke's law. And you can remove the proportionality and put an equal sign, but what you have to do is that you have to then add a constant to it. And this constant is equal to stress divided by strain, and this constant is called modulus of elasticity. And these are stresses, these are strains, and this is, remember, we were applying forces, we were applying normal forces, so this is for the normal forces. So this is formula which is important, and this is called Hooke's law. This E is called modulus of elasticity, and this is also a material property. This is also constant. We already know this before, like for steel, for copper, for bone, we already know what Poisson ratio is, what yield stress is, what modulus of elasticity is. So we already know this. So if we know the modulus of elasticity of some material, and if we know the stress, we can calculate strain. If we know the strain, we can calculate stress. So all these things, modulus of elasticity, Poisson ratio, the stresses, ultimate stresses, yield stresses, these are called material properties. And for a particular material, we already know these properties. So we can know how the material will behave. And these are two equations. These are also equations for Hooke's law, but it's like if you consider all the forces. So before, what I did was I applied one force, and then we calculated modulus of elasticity as stresses over strain. But what happens if it's a three-dimensional and you apply forces in all different directions? Then you have stresses in different directions. So if you have stresses in different directions, then you can calculate strains by using equation 2.4. So it's a three-dimensional description of Hooke's law. But we will do one example after this, and we'll use this equation, so it's going to get clear like how we can use this equation. And if we know the strains, we can calculate stresses. So these are normal strains, normal stresses, sorry. These are normal stresses. This is Poisson ratio. These are shear stresses, but we're not going to use them here. So if you know stresses, you can calculate strains. And this E is modulus of elasticity. And if I tell you a material, for every material you already know the Poisson ratio, you already know the modulus of elasticity. So if you know the forces, you can calculate stresses. And if you know the stresses from this equation, you can calculate the strains. And you can compare the stresses with the yield stress, and you can see if our stress is more than the yield stress, then we have a problem. But if the stresses because of the forces are less than the yield stress, then I guess we are fine, the structure is safe. So these are normal strains. And this is modulus of elasticity. These are normal stresses. This is Poisson ratio. So we can do one example. So we can do example 2.1. So example 2.1 says that you have a 6061 aluminum. So that's a material. So they have already specified you the material. So if we know the material, we already know some material properties. So we already know the modulus of elasticity of material. We already know the Poisson ratio. So modulus of elasticity for this aluminum material is 10 raised to the power 4 KSI, which is kips per square inch. And the Poisson ratio is 0.33. And it's a cube. So this cube is made up of aluminium. So it's uniaxially compressed. So uniaxial mean one axis. So it is compressed in only one direction. So basically you're gonna see one force in two different loading configurations. So there are two different loading configurations, confined and unconfined, but we're gonna focus on unconfined first, and if we'll have time, we're gonna talk about confined reversion. So it's unconfined. Unconfined means like it's not compressed laterally. So it's the basic configuration. But we can see what confined is, but we're gonna talk about unconfined in this example. So there are two type of configurations. So there are two type of tests we're gonna perform. One test we will perform is called unconfined test, and another test we'll perform is called confined test. So before, when you see stress strain curves, you put a sample in a testing machine and then you applied forces. So that type of test was called unconfined. So it was not a confined test. So we're going to do something similar. So what happens in a confined test? So in confined test, a test sample is placed in a large confinement ring. So this is a test sample. This is that cube. This is 6061 aluminium cube. This one. And it's confined in a confinement ring. So this is a confinement ring. So basically what confinement ring is doing is that it's not gonna like strain in a lateral direction. So if you apply a force on a cube, so it's gonna compress, but it's not gonna expand laterally because it's confined in a confinement ring. So this is for the confined case. So in a confined test, the test sample is placed in a large confinement ring. This is confinement ring. This is a test sample. Two pistons. These are two pistons. This is one piston. This is another piston. So piston basically will help apply force. So two pistons are then used to compress the sample while confinement ring does not allow the strain in the lateral direction. So the piston will apply a force. So there are two pistons. So the piston will apply a force F y. If this is x direction, this is y direction, this is z direction. So this is force along y direction. So the piston will apply a force Fy, but you will not see a lateral strains in x and z direction. And this type of loading where you have confinement. So I'm going to just put confinement. So confinement means the sample is not allowed to strain laterally in x and z direction. You will see, so in x direction you have zero strains, and in z direction you have zero strains, because you are not letting it strain in the lateral direction because you have a confinement. But in y direction you can have a confinement. So this loading results in uniaxial strain. So this type of configuration, the confined configuration, I will say confined. This confined configuration is called uniaxial strain. Uniaxial strains mean strain only in one direction. Because you have confinement, so you will not let it strain in other two directions. So it's called a uniaxial strain. And this type of setup is called confined setup. But let's talk about unconfined. So in unconfined, so unconfined is basically simpler than the confined. So in unconfined test, a confinement ring is removed. So there is no confinement ring, there is no confinement. So the sample can strain in little x direction, z direction. And this type of, so this is called unconfined. So in unconfined, you have no confinement ring. So the force Fy will be applied. And this type of setup is called uniaxial stress, because there is stress in one direction. So the sample is initially a cube. It's a cube sample with each side being 1 inch. So the dimension is 1 inch. These are the dimensions of a cube being tested. The force Fy is 50 kips, and 1 kip is basically 1,000 pounds. So the force which is being applied is 50 kip. And the question they're asking like four questions. We have to calculate stresses in all the directions. That's part A. We have to calculate strains in all directions. We also have to calculate the forces in all directions. And we also have to calculate the lengths, like what changes in length we will observe. So let's do the unconfined case first. Unconfined case. So we have a cube and this is x-axis, this is y-axis, this is z-axis, and they've already told us the force f of y, which is equal to 50 kips. And the first question is calculate stresses in all direction, right? That's the first question. And we know like what is stress, right? Stress is force divided by area. That's the formula for stress. And this is it a shear stress or is it a normal stress? This is normal stress because this is acting perpendicular to the area. So it's making 90-degree angle. So it's a normal stress. So we have to calculate stresses in all three directions. So let's try to calculate stress in x-axis. So in stress in x-axis would be force along x-axis divided by area along x-axis. So what is a force which is acting along x-axis? Zero, yeah, zero. So you have no force which is acting on x-axis and the area, so we don't need to calculate the area. So your stress x would be equal to 0. So we have to calculate stress y, which is force acting along y direction, and the area y. So this is x area, this is y area, this is z area. And we can know the areas from the coordinate axis. So what is the force which is acting on y-axis? It's 50 and the kips, and the area is, we know the dimension is 1 inches. This is also 1 inches. This is also 1 inches. So the area is 1 multiplied 1 inch square. So the stress y is 50 kips per square inch. Yeah, yeah. Yes, 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 yes. That's a very good question, and if we will not put negative, we're going to have wrong answers later on. So yeah, so we have to put negative. And this is negative because it's it's creating compression. So whenever the force is creating compression, you're going to put negative. If we'll not put negative, we'll not get correct answers. So yeah, thank you. So now we can calculate stress at z direction, which would be force at z direction and area of z. And force we know at z direction is 0. So stress at z is also 0. So the second part is strains. So since we know stresses, we have already calculated stresses, we can use this equation and we can calculate the strains. We can also calculate the strain by using the simple formula, but since we're talking about 3 dimensions, so this is a 3-dimensional Hooke's law, so we'll use equation 2.4 to calculate the strains. And since we don't have shear forces, we're not going to have shear stresses and we're not going to have shear strains, but we'll see. So let's calculate strain in x direction. So how we can extract the equation from this is like, this is the strain in x direction, which is equal to modulus of elasticity into, we have to multiply this 1 with stress x, and then we have to multiply this Poisson ratio with stress y, which is negative Poisson ratio into stress y, and then you have to multiply this with this, so you have negative Poisson ratio into stress z. And then you have to multiply 0 with this, and this 0 with this equation, this 0 with this. So it's going to be 0, 0, 0, 0. So that's what we'll get finally. And what is stress x? 0. What is stress z? 0. We have already calculated stress x and stress z, and they came out to be 0. So finally, we have strain equal to negative Poisson ratio stress of y divided by E. So that's the final we are getting from the equation 2.4 for the strain in x direction. So we know Poisson ratio, which is 0.33. We know modulus of elasticity for aluminium, which is 10 raised to the power 4 KSI. And we know the stress along y direction, which is negative 50 KSI. So we can calculate the strains. Now we have to calculate strain along y direction, which is this value. And in order to extract the equation from the matrix, we have to multiply this value with this one, which is negative Poisson ratio stress x. And then this value will be multiplied with this value, which is plus stress y. And then this value will multiply with this value, which is negative Poisson ratio stress z. And then 0 multiplied by z, this 0 multiplied by this, 0 multiplied by this, which is 0, 0, 0. So that's what we will get for the value of strain along y direction. And we know stress x is 0, we know stress z is 0. So the final equation came out to be stress y divided by strain. We know what's the value of stress y, which is negative 50 ksi. We know the value of modulus of elasticity, which is 10 raised to the power 4 ksi. So the value of strain is negative 0.005. So the strain y is negative 0.005. These are the values of strains I'm getting along x-axis, y-axis, and z-axis. So the last question is final lengths. So we know it's a cube. We know we have a force being applied on the y direction. This is x direction, this is y direction, this is z direction. So when you apply a force and it's an unconfined situation, so in the direction where you're applying force, you're gonna get a reduction in the area. So it's gonna get compressed from both the direction along the y-axis. But it's gonna compress along the direction where force is being applied, but it's gonna get extended where force is not being applied. So you're gonna see something like that. So that's the new. So when you will apply a force in the direction you're applying force, you're gonna see compression. But in the other two directions, it's gonna stretch out. So it's gonna change shape because of the force. So the question is that we have to calculate what are the final lengths. So for example, this was the original length, which was 1 inches, but because of the force, it's gonna get reduced. So let's just say this is final length along y direction. We want to know this. And we also want to know this final length along x direction. And we also want to know this final length along, z direction. So how we can know the final length? We know the formula for strain, which is change in length divided by the original length. That's the formula for strain. And we have already calculated the strains. So from strains, we can calculate the final length. So we know what strain is. Strain is elongation divided by length, or change in length divided by original length. So what is change in length? Final length divided by what was the original length, divided by the original length. So we can rearrange this and we can try to take the final length value on one side and rest of the variables on the other side so that we can formulate the equation for the final length. So strain is final length minus what is the original length divided by length. This will go there. So you will get is equal to LF minus L. So from here you can calculate the equation for final length, which is equal to strain into original length plus original length. So if you use this equation, you can calculate final length. But this is basically equation for the strain. So strain is change in length over original length, but since we want to know what final length is, so we have just rearranged the equation to figure out what final length would be from this equation. But basically this equation is strain equation, which is change in length over original length. So if we want to calculate the final length along x direction, we will have strain in x direction and the length in x direction plus the length in x direction, original length. But the lengths are same 1 inch everywhere. So what is strain in x direction? So the strain in x direction is 0.00165, and the length in x direction, length is same everywhere, 1 inches, but we are talking about this length, original length. But this is 1 inches plus 1. So if you, so the final length along x direction would be equal to 1.00165. So if we want to calculate final length along y direction, you need strain in y direction and the length in y. So strain in y direction is negative 0.005, 1 plus 1. So the final length along y direction is equal to 0.995. Similarly, you can calculate the final length along z direction, which is equal to strain in z, length z plus Lz, which is 0.00165 into 1 plus 1. This implies that the length in z direction, final length in z direction is 1.00165. So originally the length was 1 inches, but you can see that along the x-axis, the length has increased slightly to 1.00165, and the forces are applied on the y-axis. So you can see there's a reduction in length along the y-axis where the force is applied. So the cube has changed shape. Where the force is applied, you have seen a little bit reduction in length to 0.995, and the other two lateral directions have increased in length slightly. So that's the unconfined part. And in the next lecture, we'll finish example 2.3 and 2.4. And if we will have time, we'll finish the confinement part. And hopefully, we can finish the chapter this week.